Yes, let's get started. So welcome everyone. So we are getting towards the tail end of the course, and the next few lectures will see some of the real compressors and real issues with compressors now that we feel well versed with the basics. Okay, so let's get started. Today's lecture is going to be on image compression, and the next two lectures are gonna build on the basic image compression stuff which we are gonna do today. So yeah. So let's get started with today's lecture. So first, a quick recap. So last time, the first thing we saw was like the transform coding. We like delved a little bit deeper into the idea of transform coding. We did the KLT example. And one of the main things I want you guys to remember is the two knobs which you had to play with in the transform coding. One was like, what's the block size? Oh, this color looks so bad. Okay. What's the block size for your transform? And the second was like, how much do you quantize each transform stream, right? And this is like, we saw that in the audio compressor also, where you could play with the frequency cutoff as well as the number of quantized levels. And that gives you like a variety of rate distortion points to kind of choose from. So these two are very basic knobs, will mostly be available to you in all practical compressors in some way. And so question one was based out of this. So which of the following cases do you expect vector quantization to improve the lossy compression performance? Like, in the case of IID data versus non-IID data. And if you recall, like vector quantization always improves performance. We saw that even in the KLT example. Like if you can do it, go ahead and do it. It's basically mainly because of complexity that you're not able to do it. So this is both. And then in which of the following cases do you expect transform coding to improve the lossy compression performance? And this again, we know that in the IID data, there isn't really any benefit to be drawn. Like you could have just done whatever you were doing. So it's basically in the non-IID or correlated data case. Okay. So after that, we looked into DCT. We saw that, our KLT example that, okay, it's actually a lot of work. It's not practical and efficient. And DCT was one of the practical lossy compressor. Yeah, and this is just like a reminder of what the DCT was doing. So you will have some signal, right? You can have DC. So the first one is threshold 0. So you don't even truncate. Oops, sorry. You don't even truncate your DCT. You just keep it as is. And then you can reconstruct your signal Y, right? But the way you would like to do this compression is throw away the low energy channels and components, right? And so if you have some threshold, you can zero out like all the higher frequency DCT. In that case, what you recover is this green signal instead of red signal. Something I wanted to highlight, I wasn't sure if this comment made through. Like if you look at the green signal compared to the red signal, you can see that the green signal is like a smoother version of the red one, right? So red is like a sharp triangular peak versus green is like a smoothened version. And that's expected because what you did was you basically removed all the high frequency components, correct? So this is like DCT. If you want to remember anything, it basically breaks down your input signal content into some frequency contents, and then you can throw away different frequency contents based on the statistics of the natural signal as well as what we care in terms of humans. And had a good question last class, which I think we didn't do good justice answering in class. So I have posted a much more detailed answer on it, which is like why DCT compared to DFT. The main idea is like, I'll just say like in DCT, you can show that you can get more sparse components compared to DFT. And the reason has to do with what we were saying in the class, like boundary conditions. If you want to look into the details, just look at that ED post. It's like, has much more detailed answer. Okay. And so the next two quiz questions were based out of this. So the first one was match the signals to their DCT. So you didn't have to do really anything. You had to see that like, okay, for different signals, we are just increasing the frequency. And so if you look at the DCT coefficient, your higher DCT coefficient will keep shifting towards right, because that's saying you have energy more and more in the higher frequency components, right? So here I've just arranged them in the sense of answers. You can match them on the grade scope. And then the second signal was like, okay, now we truncate the DCT for this particular red signal, where we remove the higher frequency components. And then what's the output DCT? Again, so what you would expect is that you're going to smoothen out the signal. You're removing the higher frequency. So it can't be the exact same signal. Can't be the exact same signal. It can't be this. more high frequency signal, right? This is even more high frequency than the first one. Needs to be like some smoothened version of the other signal. Yeah. Any questions? Quite straightforward, just to get you guys comfortable with DCT. And then towards the end, we talked about this audio compressor where we showed this 2 different knobs which you can play with, like different frequency cutoffs, different number of quantization levels, and at different bit rate and different distortion. One knob might make better sense in terms of optimality. Like one knob might give you better distortion for a given rate, right? So for lower bit rate, you were changing color, so you were changing the frequency cutoffs. For higher bit rate, you were changing the symbol, so you were changing the number of quantization levels. Yeah. Okay, any questions until the last lecture part? Cool, so today we are going to learn about image compression. So exciting lecture. We're going to bring together everything which we have learned so far, from lossless to lossy. And in particular, we're going to learn about JPEG basics. I don't want to say we're going to learn everything about JPEG because it has like lots of small things, but we're going to at least, after this class, hopefully you guys will be able to talk about JPEG openly as like the basic components. Okay, and a lot of these slides are basically from these resources. So in particular, this YouTube video is amazing. I'd recommend you guys check it out. Very nice animations. Okay. So let's get started. So what is an image? So this is just an example of an image from Kodak dataset. So that's an open dataset. Okay, one way to think about image really is it's just an array of pixels, right? So you have some height times width times number of channels. So you have a 3-dimensional array where each pixel, you can think of it as being represented as 8 bits. Right, so if you have some image, you can think of it as R, G, and B colors, where each pixel need not be always 8 bits, but for today's class, let's assume 8 bits. It's just like something which is an 8-bit content. Okay, so you basically have 24 bits per pixel, or 3 bytes per pixel for different channels. For different heights and widths, right? So each pixel is roughly 24 bits, not roughly exactly. Okay. So this is just how you digitally represent image. This is just a digital image. And okay, so let's try to compress this image and see like why you would even want to compress this image. So for this particular image, this is a 764 times 512 dimension. So H is 764, width is 512, and then you have 3 channels, and each pixel is represented by 1 byte. Okay, so the uncompressed size for this image is just, you'll multiply these things, right? These are the number of bytes you're storing in the image. And this turns out to be 1.1 megabyte, okay? Which is quite a lot for such a small image. Okay, so if you do JPEG compression on top of this thing, this image, like this is the reconstructed image which you get. But the size of this image is 27 kilobytes, which is, if you work out the maths, it's 40x compression. And I'm going to go back and forth between these two. Let's see. Do you guys see any difference? I went back and forth many few times. So, okay, this is uncompressed, this is JPEG. I'm going to just keep going back and forth between the 2 images. Again, I'm just going back and forth. So basically you couldn't appreciate any difference in the final reconstructed signal, but you chose like you needed 40 times less bitrate for storing the same image. So okay, we are doing something good, like this compression is working, we could have saved 40x space. But you have done this class, so you know it's actually a rate distortion trade-off. Nobody is really stopping me to compress it even further. So okay, let me try to compress it even further. And so now I compress it to like by 80x. So now my file size is, instead of 28 kilobytes, it's just 14 kilobytes. Now if I go back and forth, so this is JPEG 40x, this is JPEG with 80x. Okay. Do you see something now? Right? So as you keep decreasing the rate, you start seeing a lot of these blocky artifacts. So as to say, you see here, like you can see maybe different contours. Here on the face, you can see like different pixel values. So this makes sense. So what it says is like JPEG, when compressed even further, now you start seeing distortions which might not be acceptable, right, to the end consumer. Let me compress even more. So this is what happens at like 137x. So now this image is probably pure garbage, like no application, no situation you would probably accept it, right? So clearly JPEG couldn't compress our initial 1.1 megabyte file to something like 8 kilobyte. At that point, it's clearly not doing very well. Yeah. But JPEG is really old, right? There has been a lot of work on image compression over the years. And this is what you see, like if you compress it using one of the relatively more newer image compressor. So this is compressed using something called BPG. And again, my file size is 8 KB, so I'm working at the same 137x compression. But this is the image you guess. So again, so this was at 137x compression, same rate, the reconstructed image. And this is what BPG gives it. So I think for this one, I don't really have to go back and forth. It's quite obvious, right? So clearly, even though JPEG has stuck around for a really long time and you still have a lot of images encoded using JPEG, there is a lot of room to improve over JPEG. And we'll touch some very basic ways to improve. We'll talk about like basic BPG components also today. But then basically there are a lot of places to improve. It's like a rich field. You can improve compression. We don't really know if we have hit the optimality, so as to say, yet in terms of the design of the practical compressors. And in next lecture, actually, so BPG is still something which is in some sense traditional, where you have hand designed rules. In next lecture, we'll also learn about like ML based compressors. So if you know, like machine learning has taken the world by storm. Similarly, like you can apply machine learning to compression and get even better performances in terms of the rate distortion, really. And that will be next lecture. So wait till the next one, which will be after Thanksgiving. Okay, so this is what you get using an ML based image compressor. So again, let's go from the top. JPEG, 8 KB. BPG, a modern traditional compressor at 8 KB. ML based at 8 KB. So the differences, can you see? It's much, oh, sorry. This one jumps. Okay. I don't know if you were able to see, but the face is like much more smoother. Like we'll post these slides, go look at them. When doing image compression, it's always tricky because different displays can throw away. So it's always a good idea to look at the source material, just a general thing. Okay, so this ML-based compressor we'll learn about in next class, but the main idea is there's like a lot of room to improve your compressor, practical compressors. Right? So, first main point, like you can get incredible performance gains. Like you can get 40x to 137x gains without noticing any noticeable difference, right? That's huge. That's basically why people rarely actually store uncompressed images, right? So in fact, like if you have a camera, like something like, if you have a DSLR camera, it actually JPEG compresses your image by default. Even if it's not storing it losslessly. If you would have heard of PNGs, PNG is a lossless image compression format, but again, like JPEG is much more ubiquitous, right? Like it's just present everywhere. And that's just because why do you want to pay almost 2 orders of magnitude extra space for something which is gonna look exactly the same? There are like a bunch of different image compressors. There's something called JPEG 2000. There is something called BPG, which we're gonna talk about, but there is also AWIF. There is JPEG XL, which is actually one of the best traditional image compressors which are out there in terms of performance. And then there is ML based. But as you get better and better performance, obviously your complexity also increases. And depending on different situations, you might want to use the different compressor, right? Okay, everybody with me? Excited? Nice. And so this is a really old paper. Which introduced the JPEG compression standard. So this is from 1992. And what it says that, like, it's very interesting to look at this thing here historically. It says that majority of modern businesses and consumer usage of photographs and other types of images takes place through more traditional analog means. So in 92, you weren't really storing everything as a digital format. And the key obstacle for many applications is the vast amount of data required to represent a digital image, right? So like the uncompressed size was actually one of the main reasons people weren't even moving to digital storage of multimedia applications. And now if you look at it, you see like, okay, lot has changed. See again, like from the same paper, use of digital images often is not viable due to high storage or transmission costs, right? But we know a lot has changed since then, right? Okay. So lossy compression. Let's look at the problem definition of like what do we want to do in this particular case. So you start with some image, right? You encode, you get this JPEG file, you decode and you reconstruct something, right? So we have now looked at this rate distortion examples many times. And then your original image and reconstructed image are not exactly the same, right? And one of the important things is like how do you compare how good they are, and that was done using distortion metric. And so far we have been sticking so far our treatment of distortion has been around mean square error, right? So we developed theory around mean square error mostly. We looked at transform coding examples around mean square error. We looked at quantization, right? This is just what mean square error looks like. But let's do an exercise for images, okay? So, okay, here are 6 different images. So this A image is my source image, okay? So given the source image A, which of the following images would you prefer, like visually? So which one do you think is a better reconstruction of the image A among images B, C, D, E, and F? Again, not a trick question, just shout out. Okay, B. Does everyone agree? Or does someone feel there is some other image which is a better reconstruction of image A? Okay, B is correct, right? So it's clear, right? Like if I have to choose among B, C, D, E, F, I'll choose the compressor which gives me B, for example, at similar rate, right? Compared to C, D, E, F. Now let me ask a different question. So given this source image A, what do you think, like which of these images B, C, D, E, F would a compressor which is designed to optimize for mean square error distortion would prefer? Yes, shout it out. Okay, I see a few shrugs.
Maybe F.
Maybe F. Okay.
It looks like it's the same except a few
like salt and pepper noise kind of white and black pixels. Okay, somebody said F. Actually, this one was a trick question. All the images B, C, D, E, and F actually have the exact same mean square error as compared to the image A. So a compressor is agnostic to any of these images. Like if you are designing a compressor which optimizes for rate distortion, and as a distortion it only cares about mean square error, like all of these reconstructions are equal. But that is clearly wrong, right? Like you don't, I don't know, like B and E are clearly not, you wouldn't prefer those two reconstructions equally. They are like clearly very off. You would prefer B more. So what I want to highlight here is, even though we have been working with mean square error, that is not the right metric for a lot of multimedia compression, right? Because we as humans don't really care. We are not comparing mean square error between a reconstructed image and the original image. We have our own visual pathway which does like different things, and that's what we really care about, okay? And actually there is a lot of research which has gone into understanding human perceptual laws, like all the way from like neuroscience, psychophysics to like designing these compressors. And it's really integral, like in the sense, a lot of time, a lot of experiments, a lot of money has been spent into figuring out like, okay, how do I tune my parameters so that they are optimal for a human consumption point of view. Okay, and we'll learn more about it. So this is also another topic which is close to my heart. We'll learn more about it after the learned image compression lecture. So that will be a third follow-up lecture where we'll take a deep dive into, at least for the visual stuff, what humans care about. But for today's lecture and simplicity, let's just stick with the MSE for now, okay, which is mean square error. And what you will see is like that's what people did when they were initially designing JPEG. But then they inserted a lot of different heuristics at different places to account for that, okay, human vision acts in a certain way and MSE is flawed, so let me change some of the design parameters here and there. But that's really a rich area of field, and like you have lots of heuristics which are there. So sometimes it's very confusing if you would go look at the JPEG, certain design decisions, like why were they taken? Later on you realize, okay, there were some subjective experiments which were done to figure out those parameters to actually determine it. But again, like mostly it's MSE, which we are optimizing for now. Okay, so what are the problem caveats? And it's basically, so just certain things, because we have looked at various different settings. So the setting really is like typically we are compressing a single image and not really a group of images. If you are compressing a group of images, you can probably do something better than just compressing a single image alone. So since you are basically working with single image, non-asymptotic performance of a lot of these techniques is really important because you don't really have infinite data which you are working with. So you have finite data. All these artifacts do show up in compressors in different ways. And also data is most likely non-stationary, right? So it's not really, you're not gonna get IID pixel values really in the images, right? So transform, for example, is going to be a big help to decorrelate these pixel values. And actually we'll be using all the tools we know so far to build this compressor, right? So like on the lossy side, we know about scalar quantization, which is extremely fast, but not the best. We know about vector quantization, which is extremely good, but gets really slow as the number of dimension increases. We know about transform coding, where we decorrelate the data and then use the simpler scalar quantizer. And finally, we haven't really explicitly talked about predictive coding, but it's not that hard a concept to think about, right? Like, so when you are doing lossy compression, maybe you can predict the current symbol based on the past symbol, and just do the subtraction. And if you can do a really good job at predicting, you need to spend less bits to encode it. So this goes back to the context-based lecture, right? Like if you have a better probability model, you have a better compressor, like if you recall. And we'll have a quiz question in today, so you can just revise your predictive coding in terms of lossy compressor, but it's not really a fancy idea, right? You can use the past, it's like we have looked at it in homework 3, we have looked at it in lectures, you can use the past context so as to say to predict the next one, and that will improve the performance in terms of lossy compressor. And basically all of these tools are used for making your image compressor. Cool. So now that we have set up the problem, let's think about how we would compress this image. So your image, again, is just an array of pixels, height, width, some number of channels, for now RGB. Any thoughts? Like throughout the first obvious thought, like what can you do to compress this image? Let's not even worry about distortion for now. Let's just think about what can be decent ways to compress. Okay, one idea I got was large block of colors. Any others? We'll use that. Even more simpler, maybe. Or it's okay, just throw out ideas. We'll see them in next few slides, mostly, or during the next hour. Any other thoughts? Like, so all of you know a lot about compressors now. Don't worry. You just got this HWC kind of data. Don't even think it's image data. You got this array. what can you do? No takers? Okay. Really the first obvious, simplest thing you can do is throw away half of the data in terms of height and width, right? You can just downsample the original image, which basically goes from making your image from HWC to maybe something like H by D, W by D, and C. Okay? So for example here, I just reduce this image in terms of height and width by half. And immediately I have got 4x compression, right? I have basically thrown away, like I have reduced the rectangular number of pixels by 1/4. So like this gives you 1/4 of the compression, 4x the compression. And then what do you do at the decoder? You need to do the inverse operation. So this is lossy compression, right? So we lost information when we did this downsampling. What you can do at the decoder is, like, if you know about upsampling techniques and signal processing, things like, I'm just gonna throw the terms, it's okay if you know, if you don't know, it's fine. You just think you can upsample, but you can do, like, I don't know, bicubic interpolation, Lanczos interpolation, things like that, which is just filling out values between two particular discretized signals. You can do that at the decoder, and that will recover you something of the original size. And then you can compute the MSE between two, which will give you some distortion, right? And then you can obviously, like, play with the rate distortion by changing this factor D. So instead of 2, I could have done 3, 4, 8, 16. Nobody's really stopping me. And this sounds really stupid, right? Like, oh, I just reduced it by half or by 16. But actually this is one of, I would say, the primary ways in your rate distortion curves are even made in image compressors. So if you think about, like, images, what has really happened? Like, we used to talk about, let's take example of YouTube. We used to have 240p, 360p, 480p. Like, we used to have these terms. So these were basically referring to the height and width of your images or videos, right? And as you keep increasing the resolution, you have much higher quality videos and images. Like 4K, for example, that's like amazingly detailed image, but then obviously you are paying the cost in terms of rate, right? And many times, maybe if you just have, I don't know, a very dull scene, you are not really watching, I don't know, your favorite action movie, it's probably okay to just watch it in 720p or 1080p if you're watching, I don't know, not a nature documentary, a boring documentary maybe, right? And so in practice, so we're not going to talk much about it, but in practice, again, this is one really common way in which people do multimedia compression. Like, you would downsample your 4K image to something like 720p, and then your TV on the other end, when it receives 720p, it upsamples it to something like 4K. And then obviously it's not the exact same thing which maybe the director wanted to show you, or the whatever, if you were clicking a photo, wanted to show you, but you use it all the time. So it's one extra knob which we didn't really talk about during transform coding, but you have this knob when you are building this rate distortion trade-off curves for any multimedia. Similarly, for audio, you could have, for example, change the sampling rate, things like that, right? So you always have that option. So something to keep in mind. Okay, so this idea was like, okay, we haven't really talked about it, but very basic and simple. But another simple idea is, like, you can just quantize, right? So let's just quantize the channels. Now we'll stick with approaches where you don't change the height and width. So you want to keep the height and width the same, but we want to do something about the channel dimension. So another simple idea is you quantize this 3-dimensional vector RGB, right? And this we have seen, and now it's just basically quantizing the color values, correct? And so, okay, so in this image, we had 3-dimensional, each of these were 8 bits, right? So RGB, each of this was 8-bit. But now I can just represent this image using only 256 colors. Okay, so earlier I had options of 2 raised to 8 times 2 raised to 8 times 2 raised to 8, because I can have 2 raised to 8 possible values of R, 2 raised to 8 possible values of G, 2 raised to 8 possible values of B, and each of them represents a different color. But instead of using these many colors, this is how this image looks like if you just represent it using 256 colors. Again, I like to do this because it clearly shows me if there is any change between two images. So again, I'm going back and forth between the original image and the quantized image. Personally, I don't see much difference. So again, just doing this basic quantization gave us around 3x compression. Okay? Without really bringing any distortion in terms of how the image looks like. And the main idea here is like, obviously we don't have like whatever this number turns out to be, 2 raised to 24. We don't really need these many colors to represent this image. There are like lots of colors which will just never happen. Like those are just not natural. So maybe we could have thrown away. We didn't really have to consider that big a color palette to start with. So you can keep reducing it. So this is when you keep 256 number of colors. This is how the image looks like when you keep just 16 colors. So like 6x compression. At this point, you start seeing some artifacts, right? Like it's actually quite obvious. Because now you only have 16 colors, you can't really express that image as well. So again, examples of rate distortion, right? You can keep throwing away more data, you'll get lesser quality. Okay, so this is like one idea, and this is also called like, so we just did like vector quantization on the color channels. It's sometimes also called color quantization. It was like one of the first ideas which was explored in this field. Okay, but how can we improve? So what else can we do in this particular scenario? If this is the image you are trying to compress, so far we used that, okay, our images don't really have that many diverse colors. What else can you use if you were trying to compress this? Yeah, your face seems like you want to answer.
You don't have to store the same color many times.
Yeah.
Several pixels are of the same color, you store one and prefer like having a pointer point to that color.
Yeah, so that's exactly what we did in quantization, right? So we made a codebook vector and we pointed back to one of the closest codebook vector for each pixel. But you are almost there. So what you said was like nearby pixels might have the same color, right? But actually, okay, even if they don't have the same color, they are somewhat smooth, right? Like natural images, it's not going to happen that I'm gonna suddenly have those black and white noisy images which we have seen. Natural images are smooth, like all the colors, like the scene which we are seeing is smoothly changing, right? So the pixels nearby are actually highly correlated, right? And this is an example. So these are just zoomed out shots from the image. So this is like this spot, this is this spot, this is this spot. And you can clearly see that a lot of these pixels are like highly correlated. So if you basically stick to some local, you can exploit the fact that I probably need even fewer colors, or maybe get away with like representing all of them with a single color, so as to say. Right? So the idea is really like, let's try to exploit I don't know what happened. Let's try to exploit the correlation between neighboring pixels. So that's like the next obvious idea. And this is an example. So this is called color cell compression. It's a technique which, again, so all of these are like really old methods. This one is like 1984. Where what people did was like, they said, okay, we'll take a 4x4 block. Okay, so that means like this, where was that? Sorry. This thing is 4x4, let's say, instead of whatever it is. And we'll represent each of these 4x4 block by 2 colors. And on the left, you see the original image. And on the right, you see the reconstructed image using just 2 colors among 256 for each 4x4 block. And this exploits the fact that within my 4x4 block, my pixels are highly correlated. So maybe I can just get away with having 2 colors. I don't really have to represent it with having huge number of colors. And again, as you can see, like both these images, at least to me, if I'm seeing from far away, looks okay. right? If you are careful, you'll see some differences, but really it's mostly okay. And the idea really is like, basically it effectively gives you like 2 bits per pixel. And that's because, so for each 4x4 block, we first need to store the 2 colors, right, for that block. So you need 16 bits per block. But then we also need to decide, like mentioned that, oh, you need to have some pointer to tell you like, okay, which color does this pixel belong to, right? So you also need to store a bit per pixel to tell you, okay, my first pixel belongs to color 1, my second pixel belongs to color 2, so on and so forth. Okay, so you need 16 bits for storing that sort of pointer, 16 bits for storing the color. So at the end you need 32 bits for how many? 4x4 blocks. So, sorry, 32 bits for 4x4 block. So that's like 2 bit per pixel, right? So recall, we started from 2 raised to 24 bits per pixel, and now we have gotten down to something like just 2 bits per pixel. And for certain images, this compression, like as you can see for this particular example, it's really good. Again, very basic idea of quantization. Okay, everyone with me? Like, people understanding what's happening? Okay, good. But again, like if now I zoom in on this particular image, now you would see like certain artifacts. So for example, you can see this eye. So this is like the same 2 images just zoomed in, and you can now see that, oh, see like 2 things. First, my orange color became yellow, and then you see this red pixel aberrations. And that's basically happening because, again, I'm just representing my each 16 block by 2 unique colors, right? So you will have some distortion, and again, depending on the specific image and setting you are working with, might be acceptable or might not be acceptable. Okay, so this was one way, but it sounded very, it was very heuristic, right? Like why 2 colors, why 4x4, like sure, like we could have tried many different things. And the main thing which it was trying to really do, like the reason it was able to get any compression was because it was exploiting the spatial correlation in the data, right? But we know better ways on how to handle with the correlation in the data, right? We have actually spent some time looking into it, which can help us decorrelate this data and then allow us to use a simpler and standard techniques of scalar quantization. And the idea is transform coding, right? Okay, so this is the block diagram for the transform coding, but now for images. Again, we have seen this time and again in the past 2 lectures. You start with some original image. You start with some original image. You convert it into transform coefficients. You quantize and do other things like lossless compressor, use an entropy coder. That gives you quantized transform coefficients, and then you inverse transform it to reconstruct the block. The only addition now is, so far we were working with 1D transforms, right? A transform was just a vector. But now for images, we can think of this as 2D. Let's work with grayscale image for now, for a second. So now you have 2D images, right? So what you have to do is, okay, first variable is your block size. So you figure out like, okay, what's the B by B size block on which I'm going to run my transform. So that's equivalent to, for example, that parameter 2, which we looked at in the last class. That gives you one of the original image block, and then you do some transform on it. And then when you inverse transform on it, you again get a 2-dimensional block. So the only sort of new addition is now your transforms are acting on 2-dimensional signal instead of 1-dimensional signals. And then you can use it to reconstruct the original image. Okay, everyone comfortable? Okay. So just to recall, a transform was like we were thinking of only linear transforms so far, right? We have restricted ourselves to thinking about linear invertible transforms. So in this case, what has changed is now your A is actually the same as the transform. But now your input X is a matrix. Earlier it used to be a vector. So now it's an image block of size n cross n. But you can also arrange it as a column vector, right? So no one is stopping you. You can figure out how to linearize this. And now your transform matrix is something which is then n square by n square, right? If you have n by n block, that basically means you have n square dimensional vector. And so your transform matrix is now n square by n square, and that gives you again n by n transformed components. And when you do inverse, you just inverse it. And again, we are looking at orthonormal transforms, so you don't actually have to run the inverse. You can just take the transpose, and that's much more efficient. Computing inverse is like n cube if you have n by n matrix. Cool. So that's basically the only addition to what we have seen so far in class. And again, just a reminder, so this is an image we saw in the notebook during the last class. So let's just recall what our 1D DCT vectors actually looked like. So in this case, our example was with block size n, and our DCT matrix was just n square, where the example I showed you was with block size 8. And so this is what your DCT transform matrix looked like. And we briefly mentioned, if you look at the first row, which will give you the first transform component, that's basically the DC value. That's basically the average value of whatever input pixel blocks you are giving it. Sometimes this average value, and you will hear this term DC component in a lot of multimedia compressors, basically refers to the average value. The origin of this DC is like direct current if you have done electrical engineering at some point. But it's a very commonly used term. So if you see DC component, don't get confused. It's just people saying average value. Okay. And then you have, for the other bits of transform values, you have these higher frequency components, right? So that's what DCT was doing. As you were going higher and higher here, you were accounting for higher and higher frequency components, right? And again, sorry, I didn't write it here, but these are referred to as AC components sometime. So everything above except DC, like the first component, which is the average, is sometimes referred to as AC components, again, referring to alternating current. So you have some frequency behavior in this thing. Okay, so this was the case for 1D DCT vectors. Now, I'm curious how the 2D DCT vectors would look like. Again, sorry, I should have highlighted. Another thing to notice here, right, was as you move down, your signal was higher and higher frequency, right? So you can see this had more yellow values in the first half than second, and this seemed like there is some split here, more higher and higher frequency components, right? And this is how your now DCT transform matrix looks like for the 2D DCT transform. So first thing is your block size now is n by n square. So your DCT matrix is n square times n square, which we just saw. So here it's again an example with 8 by 8. So this is like your first transform, and you have basically an 8 by 8 matrix. And each of them is individually 8 by 8. I don't know if it's visible, is it? But you got the idea. Okay. So this is your DCT transform is now going to be n square matrices, each of n square size. Okay. And one way to think about these 2D DCT is like it's exact generalization of 1D DCT, where we were taking these quantized cosine values, but now for a 2D cosine transform, 2D cosine wave. And one very nice thing about 2D DCT is that it's separable. So you can basically get 2D DCT transform by just doing a 1D DCT transform along one of the dimension, and then again 1D DCT transform along the other dimension. Okay? We'll see this idea in more detail, so don't worry about it, but this is really one of the very nice properties about 2D DCT, that it's a separable transform. Okay? So let's try to interpret this this set of matrices like 2D DCT. Let's try to understand what it's really doing. Okay. Any thoughts? Like, do you see some patterns here for these 8x8 matrix blocks? Again, not a trick question. Like, I'm sure there are, yeah, some patterns there. You can just shout it out.
The first row of matrices kind of has the same pattern as we saw for 1D, where we have like just flat for the first matrix, and the next one is like it goes from low to high, and then increasing frequency after that.
Yeah. Okay. Exactly. So Sean answered that. Okay. First row of this series of matrices seems very familiar. It's like it has similar vibes to the DCT 1D matrix, where the first one seems just like a white, like just containing DC components, and as you move towards right, it seems like, okay, you have vertical bars which have sort of higher and higher frequency as you are moving towards the right. So, okay, great observation. Any other observation?
The column is the same way.
Exactly. So obviously now if you look at just the first column, you see similar pattern, but now instead of vertical stripes, you have horizontal stripes, right? What do you think is happening as you are moving towards the, what will it be for you guys, bottom right?
It seems like a product of like the first row and the first column.
So if you look at like just the first column, it seems like your frequency is increasing in the horizontal stripes. If you look just at the first row, it seems your frequency is increasing for the vertical stripes. And if you kind of go look down along the diagonal, it seems like you have sort of mixed, right? Your frequency is increasing along both X and Y directions, so as to say. So like, but if you look maybe to this guy here, it seems it has more frequency along the vertical dimension than along the horizontal dimension, which sort of matches the same guy at the top. And so essentially what this 2D DCT transform is doing, as what we would intuitively think, is it's capturing frequency in horizontal and vertical directions, right? So again, if this hand wavy treatment, it's still hand wavy, but okay, if this literal hand wavy treatment wasn't good. So okay, the first component here, the first matrix, is just the average value again. So this is like the DC component. So you just see it's pure white. It's just giving you the average value of that block. As you move towards the right, your horizontal frequencies are increasing, right? So if your vertical stripes are increasing in are coming up in higher and higher frequency, that's to say like the x-axis frequency is increasing. Similarly, if you're along the column, as your horizontal stripes are increasing in frequency, that's to say the vertical frequencies are increasing. And as you go towards the, again, sorry, what is this, bottom right, you're basically mixing, right? And depending on where you are in the array, you can think about whether it has more higher frequency component along the X or higher frequency component along the Y. Cool? Everybody comfortable with the idea? Okay, so let's look at a few examples. So this, on the left, I'm going to show some image blocks. These are, I think, 24. This is actually 24 by 32, but it's okay. It's not really, I don't really need to make it square. And on the right, I'm going to show the 2D DCT transform, basically, of these things. So for the constant image, and yellow is high, blue is low. So dark blue is 0, more yellow, higher the value of that DCT component. So for a constant image, you just see a blip at DC value, everything else is 0. For this image where you now see some frequency along the X, and it's a very specific one, you see again a delta function, so as to say only one component. Here is 1, everything else is 0, which is what we expected. Now if you have some other patterns of images, again like, so these are like exact DCT component basis. So these are like the exact DCT component matrices. You again see like blips. So this whole image, if you were converting it into some transform, like if you were converting it into transform components using 2D DCT, you actually get an extremely sparse signal, right? You basically get only one non-zero value. So again, going back to our compressor hat, wearing a compressor hat, that's very good. Like I can throw away all the different components and just keep that. And then instead of compressing these 64 components, I could just compress one. So this is how like the same idea of decorrelation and energy compaction at play. Let's look at maybe some more realistic examples. So this is actually a very popular image. I'm not sure what's the source of this image, but I've seen it a lot in classical image processing classes and all. Let's try to look at the DCT components for 3 different blocks. So again, this is this. This checkerboard pattern is here, and then these are just like those small blocks from this image. And let's try to look at the DCT pattern for this. And so for this first image, so this is like just this particular region in the image. What I see is now my DCT spectrum looks like this. So again, you see like most of the values are 0, but now you don't really have, in practice, you won't really have just a single component with non-zero value, right? You'll have multiple of them. And so this is what you see, but again, your DCT is extremely sparse. And why do you expect that? So let's again recall why DCT was a good transform, right? It's because your natural signals don't really have a lot of high frequency component, right? And so this is what you are seeing in this, for example, this particular image or this particular example, that your natural images are really smoothly varying. You don't really have any higher frequency component. So this is like another block from that image. And again, you see your DCT is DCT is sparse. But now you see the colors are more spread out along the x-axis, and y-axis is basically all 0. And do you expect that? Like, does it make sense? Right. I see quite a few nodding heads. It does, right? Because if you look at this image, it seems it has some stripes which are going in the horizontal direction, and DCT is picking that up, basically. But still the signal is sparse. And now if you look at that checkerboard kind of thing where there was this tablecloth kind of plug, now you see much more higher frequency components. There is like a lot more action happening. But I would say, interestingly, it's still very sparse. You would have expected this signal, like it has a lot of high frequency component to be like involving a lot of stuff, but no. And that's because our basis vectors, which are composed of this higher DCT, have these higher frequency components, right? So this image can be represented by linear combination of just these guys and weights. Finally, if you had like a noisy image, right? So this is an image which you probably don't expect to see in nature, right? It's basically just noise. If you have a really noisy image, then, oh, sorry, this shouldn't say sparse. DCT is not sparse. Right? Now if you have noise, then you see a lot of these different checkerboards. Okay. People comfortable with 2D DCT? So let's look at an example. So now we talked about 2D DCT. So you know what I'm gonna do next? I'm gonna truncate using this 2D DCT. That's what we did last time also with 1D DCT, right? That's how we will exploit it for compressor. And so this is just a puppy. And you can see like when you just keep the 0 DCT component, so basically just the 0 at DC component, this is your reconstruction, which is expected here. At that point, you're just basically storing the average value of pixel in that block. As I increase my DCT components, so basically what I'm doing is I'm zeroing out all the values in those components which are above this. So this is my threshold. So if I keep just like the first few DCT values, this is my reconstruction. And already you see it has gotten the structure of the dog already, right? And this is just with 2 DCT components in this case. So we zeroed out 62 DCT components and still could recover this. Maybe I can add more, right? So at around taking first 8 DCT components, now my reconstruction looks really nice, right? And so this is the power of essentially transform coding, right? You could transform which decorrelated and did your energy compaction, and that allowed you to really throw away a lot of frequency components. And there will be a question on homework for you guys to play with these things for image compressor, tying together transform coding, so it'll be fun, but basic idea is basically, you saw what the basic idea of the transform coding is. And so I'm not going to repeat this, but I think we have seen, now I've repeated this many times, for natural images, your DCT is sparse, your energy is concentrated in the lower frequencies. This basically gives you this energy compaction, which you can exploit to do smarter compression. And this is really one of the key observation of JPEG compression compared to like color quantization or other things which we saw before. Okay? Yeah, everyone with me? Any questions? Cool. So let's look at the JPEG compressor now. How your JPEG compressor works is you first have your image, you do some color treatment, and then you have this JPEG encoder, which consists of forward DCT, quantization, and lossless encoder, which finally gives you the JPEG. Like, is this part familiar? We actually talked about it in last class, right? Like, this is like the basic block of a lot of, I would say, bare bones practical lossy compressor consists of these 3 steps, right? You do some transform coding, you do some quantization, you do some entropy coding on top of it. So again, I want to highlight that a lot of design decisions for JPEG are based on the ideas of how human vision properties work, and we'll have a dedicated lecture on it. So today's lecture will not cover a lot of these things. So take it with a pinch of salt. It's not really JPEG, it's like, let's say, a simplified JPEG at best. Okay. So the first step during JPEG compression is this color transform and subsampling. And let's see, why do we need to do this? So if you look at the RGB components of an image, even the RGB components are extremely correlated, right? Like, they have this same spatial correlation. And why do you want to store them independently? So you would like to somehow exploit this. And one way to exploit this is you convert this RGB, it's called color space, to something called, for now, Y-CRCB, color space, which basically decorrelates this color component. The main idea really is you can use one channel to actually store the average values, which basically captures the structure. And then you can use the other 2 channels. These are also called like chroma channels. So your Y is also called luma channel sometimes. And your CRCB are called chroma channels. Chroma just means color, right? So you can decorrelate your image from RGB to one channel just storing the average value. So in this case, you can see like this mountain structure is translated mostly to the grayscale, in some sense, image of this RGB channel. And then the chroma components take into account the color, which together will determine, okay, how this is supposed to look like. Again, luma channel is just the average value for now. Let's think. It's not exactly the average value, but for today's lecture, let's assume it's the average value. So this is the idea of color transform. Makes sense why you would like to do that. It immediately improves like the correlation across the colors, like it decorrelates them. And then the second part is called chroma subsampling. And this now combines the fact of the subsampling idea which we saw at the beginning of the class, which is, let's say this is your image in RGB space. You first convert it into YUV. So this, you can see it's like the grayscale sort of version of this image. These 2 contain some color ideas. So all of these are single channel. and then you selectively downsample just the chroma channels. Okay? And the main idea really is that, oh, my luma channel already contains most of the structure. I can tackle more loss in the colors, right? I'm more sensitive to if you change the structure compared to if you change the color that much. Recall like when we were doing color quantization and transform, I could actually get away with like reducing a lot of color information without introducing a lot of new distortion. And we're gonna talk about like what this 420 means in the human lecture, because a lot of these ideas are also derived from how human vision works, really, like why you could do this. But this is essentially the idea of chroma subsampling. So first step is you convert it into YUV, and then you do more subsampling for UV than Y. You can differentiably do that. And this is really like this is an example of how this works out in practice in terms of number, why this is again a very simple but powerful idea. So this is an image at 429 kb. And when you JPEG compress this image without any downsampling, so all these 4 images are roughly equal quality, so you can see they look roughly same distortion. When I just do JPEG compression without any downsampling, I get 323 kb. Okay? But when I do this chroma downsampling, first of all, I get some advantage by just downsampling. So that's what we expect. That was the first idea we started with. If you downsample, you'll get some compression. And if you look at these 2 images, they look very similar. So even when you like downsample the chroma part, it's not really visible in this case. But even more advantages comes after that when you apply JPEG, like a bare bones lossless compressor on top of this chroma subsampled image. Now you could get an image which looks very similar but takes only 176 kilobytes. Remember, without downsampling it was taking 323, now it's like almost half. So what I want to say is like you're not only gaining benefit by throwing away the samples, you're actually gaining a lot of benefit because now once you throw away the samples, your images are much more correlated, right? If you have a much bigger array, pixel array, that introduces more details, that will have more high frequency component. But if you already downsample it, that's like low pass filtering. You have introduced much more correlation in the data which your compressor downstream can exploit. So it's like a win really in 2 different ways. One, you throw away the data. Second, oh, my compressor can now compress better while basically maintaining very similar quality. So it's like really powerful. You have already gone from 429 to something like 176 kilobyte without really doing much. And so the first step really is like this color so I'm just now adding some details like so that when somebody comes and talks to you about these things, you can understand that. So we said RGB to YCBCR. Sometimes you might hear terms like Y-CBCR, YUV, Y-UV. All of these are equivalent for now. But if you want to learn more about this, you can come talk to me. All of this has to do with a lot of historical context and how color spaces work, things like that. And the core reason for this, why this whole thing works fine, is there isn't really much, especially like this chroma downsampling part. It's actually our first exposure to a very concrete design decision which was taken based on how human vision works. And we were able to do this because our human vision isn't really as sensitive to colors compared to the luma component. So we already started exploiting that, hey, MSE is not the only thing which matters. Actually, at the end, this is going to be consumed by humans. And we'll learn about these reasons in the next class. Okay, so let's continue then. So we talked about the color treatment. Let's go look into the details of our more familiar block. Any questions on the color treatment and chroma subsampling? No. Okay, so let's continue. So now we'll just basically look into each of these blocks. You already know, so I'll just fill in some more details for you guys on how exactly this works in JPEG. Okay, so step 1, we want to do 2D block DCT, right? So you want to convert your image into blocks. So in JPEG, you basically take 8x8 block sizes. So let's say this is your image. You cut it into 8x8 blocks, and then you subtract 128 128 from it. That's just to center the pixels. So 8 bits is 256 unique values. When you subtract 128, that just centers all the pixels. And so this, for example, is this for instance is an example of one input 8x8 blocks, and this can have like different values. So 220. So let's work with grayscale image at this point because we have already done color treatment and everything before. So now we can imagine we just have one channel, right? So once you look at maybe this particular block in this image, it looks something like this. And what is this grayscale image? It's at the end of the day some uint 8 integers, right? So you have some values 221 to all the way 94. So 94 is dark. 221 or 230 are like brighter values. Okay, so you have got, this is your 1 8x8 block. And then the second step is like after you have converted your input 8x8 block and zero centered it, you run the 2D DCT, which we talked about. And that will again give you an 8x8 transformed block, right? And the way you do it is what I was saying earlier, that one good thing about 2D DCT is that it's separable. So you can basically apply 1D DCT along the x-axis and 1D DCT along the y-axis, and that will give you the 2D DCT. And we saw that even when we looked at that 8x8 matrix blocks, like it seemed like it was completely separable around the 2 dimensions. So the way you work around this is once you have this input 8x8 block, you first do DCT, 1D DCT along the rows. So I'll just do DCT along the first row, I'll do the DCT along the second row, so on and so forth. And that will give me this 1D DCT along X. And then I'll take this input of 1D DCT along X. And next thing I'll do is I'll just do DCT across columns. So I'll do DCT across the first column, 1D DCT across the first column, second column, so on and so forth. And that eventually gives me, both these steps combined, gives me this 2D DCT. Yeah.
Sorry, I got a little lost before. Is your 8x8 block 8 pixels by 8 pixels, or is it chopping the whole image up into 8x8?
So it is 8x8 pixels, so your image might be larger, right? So this is your image. You chop it up into various 8x8 pixels blocks, and then now you are working with one block. You are looking at one 8x8 block. And so these are like the pixel values within that one 8x8 block. Yeah. This is really important. This shows up in image compression everywhere. Okay, and so now, and then you like zero centered it and you did this 2D DCT transform. So at this step we have the transform components, right? So this is just showing like you started with this single block and you'll get some values, and now your 2D DCT transform might have positive or negative values. This is when you're implementing all of these things becomes important, because now you have to take care of the sign also in your actual implementation. Okay, so that's all I have to say about the 2D DCT transform part for the JPEG. So things to remember is it's very efficient, separable, right? What that means is your complexity is instead of 64 by 64, right? Because it was n square times n square, that was the metric. So instead of 64 by 64, you can now get away with 2 8x8 transforms. So you have drastically reduced the number of operations which you have to do just because this transform was separable, right? So this is just, I saw one confused face at least. So this is n, our block size was n, and so that's 8x8. And so this was n square times n square, and this is just 2 times n square, because 1D DCT takes cost is n square, whereas 2D DCT the cost is n square times n square, right? So that's a huge savings just because it was 2D. Okay, so continuing, after you have done the 2D transform, you want to do some sort of quantization. That's really how you trade off between rate and distortion. This step is also called like rate controller in some compressors. So just throwing out a name, but again, you can, like if you hear rate controller somewhere, don't get lost like what happened. That's just basically saying how you trade off the rate with distortion. How this works out in JPEG is you actually have these fixed quantization tables. And all you do is like, you're basically doing uniform quantization, right? Like scalar quantization of each channel. So the way you can do it is you just divide by these numbers and you store the integer value of those numbers. So for each element, so here I have 338, I'll divide it by 16, I'll store the integer value. Similarly, here I have minus 10, I'll divide it by 99, and that's basically going to lead to 0 because I don't have really any remainder. Okay, and you basically can take off the sign, so you will see the quantized DCT. You can keep the sign aside and just take the number and divide it. And so basically, if you have a higher quantization table value, and these quantization table values have been predetermined, again, if you have to guess like how they have been predetermined, that's a lot of fine tuning on like human experiments and what works for us. But it still has a very obvious pattern, which is if you look at the elements towards the bottom right, they are much higher than elements towards the top left. And that's expected because you want to more strongly quantize the higher frequency components compared to the lower frequency components. Again, recall all your water filling, all the different ideas which we have looked at. Right? So this is how JPEG really is comparing the rate distortion. And so you basically have different quantization table for different compression rate. It's not really a fixed. Once you fix this quantization table, your rate is sort of fixed, right? So you have basically these different quantization tables for different quantization rate. And again, like the values of these tables are designed based on like this water filling idea and human vision properties. Again, like I think one of the questions in the next homework will make you go through these things yourself, so you'll appreciate this idea a bit better. And then the final step is really the lossless encoding, right? We finally got these quantized integer values, but now this is a discrete signal. I can losslessly compress it because now you see there are like lots of, for example, zeros in there, so I should be able to compress it better. And for this step, JPEG uses a modified Huffman encoding. And so it's quite complicated. It changes quite a lot, but the main idea really is like what JPEG does is it does run length encoding followed by Huffman table. So if you are not aware of the run length encoding idea, the idea really is, so first of all, you go in a zigzag fashion. And the reason you go in a zigzag fashion in images is just because they are more correlated when you go in a zigzag fashion than if you were just going along X and then you go up. These two pixels are really far away, so they are less correlated. So you go in this zigzag format, and then you just look at the symbols. Okay, so first I have 90, then 90, okay, this is done. Then it's followed by minus 40. Then I see a 0. Right? And then I see 2 more zeros, then I see 5. So I see this, and so on and so forth. But this I can actually write it as 90 minus 40, and then I can say, oh, I had 3 zeros. And then I had 5, and so on and so forth. I don't really need to care for 0 as this. So this is like the vanilla run length encoding idea. So run length encoding. And in JPEG, actually, you go one step further. So this is like a variable length encoder. In JPEG, you actually go one step further, and you actually store these triplets. So you see like 90 showing up, but then it has 2 more, like a tuple before it. And what this tuple is really saying is that, so 90, so the third number is just the value. So 90 minus 45, like the non-zero values. The first number is the number of zeros preceding that value. So there was no 0 preceding 90, so my first number is 0 here. No 0 preceding minus 40, I have 0 here. Oh, before 5 I have, oh sorry, the second tuple. No wait, yeah. Did I do something? Oh yeah, sorry. I actually did wrong run length encoding here. You don't really go in this zigzag manner. You actually go in sort of you go in this zigzag manner. Okay, so I think I made a mistake by just going in this zigzag manner, the zigzag manner I showed, but that was just to give you the idea of run length encoding. So here in our example, there is only 1 0 preceding 5. So you have that. And then the second number actually is the length of the integer in bits. So the second number here, it's basically number of bits in unary encoding of 90. So that's just saying log 2 of whatever your third number in the triplet is, right? And so the idea of doing this really is that if you were to, so recall the Huffman code, go back to the question, homework 1, right? If you were to just use a vanilla Huffman code for this thing, quite a lot of different values. You can have 0 to 255 unique values, and your Huffman code actually can have a very high depth, depending on the probabilities and how you are merging these symbols, right? It can be extremely unbalanced, and you don't really know what that tree looks like beforehand, right? So recall, like one way to get over that is, since this is a variable length code, another way to do Huffman encoding on variable length code is I can store the length separately, which is just the number of bits which I need to read, for example, for 90. And then I can run the Huffman encoding on just this length. And Shubham also covered it briefly in gzip in a slightly different setting, but that's basically the idea. So that reduces the Huffman table encoding complexity by quite a lot. Yeah. And then we are not going to go into this, but there are even more concepts around entropy coding, which is like, it's quite complicated. You need to take care of the signs. You actually do different paths for DC versus AC. So in the sense, you have different Huffman encoding tables for the DC component compared to the AC components. And the reason really is like you basically have much more smoother variation in the average component than the AC. And then we also know that the average values are more important to preserve, right? Like similar going back to the luma and chroma. Like how you combine across blocks, it's actually also different for DC and AC. For DC, you actually combine across blocks. For AC, you don't combine across blocks. So there are lots of, like, coding up an actual JPEG end-to-end it's no joke. Like, people spend a lot of time and did this, but we can still appreciate all the main ideas here, right? And so this is like really the summary for JPEG compression, which is the first step was color conversion. So your RGB is converted to YUV. Your color channel is such that like each color channel is encoded independently of each other, like we do YUV independent. And then we went on to do our bare bones lossy compressor. So you did like block coding where JPEG encodes each 8x8 block independently. And again, this is except the DC coefficient. So be careful, like DC coefficient, you do encode across block, but otherwise you do independent encoding of blocks. And then finally, JPEG uses Huffman, but in practice, you also have support for arithmetic coding, but it's hardly used. Okay. And so, like, this is our original image, which we started with, like 40x uncompressed. And this is the same image with 80x compressed using JPEG. And in this image, again, now you can see like all these artifacts, right, which we pointed out. And now you can actually explain some of these artifacts. If you see, a lot of these artifacts looks really like square-shaped, right? Why are they square-shaped? Because now we are doing things independently in each 8x8 block. So like each 8x8 block is processed independently, and you can have these discontinuities which are quite obvious to the viewer, right? Go look at it at home. So this is just like a JPEG decoder specification. We looked at the encoder, but the decoder actually needs to read these bits. And so there are like lots of, again, star marks on, you have to tell it how many heights and widths of the pixels which are coming in. You have to encode the Huffman tables. Remember, again, the homework 1 problem, you either need to communicate the Huffman tables or you need to give enough information so that the Huffman tables can be built. So a lot of stuff is like around like how the Huffman tables is built. You have to store your quantization tables. And then here is your image data in this whole thing. But this is just like a bitstream specification of what the JPEG looks like. Cool. Any questions? So at this point, we understand JPEG. We understand a very basic traditional lossy compressor. But there are obvious ideas on how it can be improved, right? Like it had It was very good at the time it was designed. People had lots of computational limitations, and it actually performs great, but you can improve it. And so BPG kind of improves it by doing two main things. One, in JPEG we had 8 by 8 blocks, right? But BPG basically allows for larger blocks as well as variable size blocks. So you don't really stick to 8 by 8. Sometimes maybe the image has more correlation in a bigger block size compared to the smaller block size, right? And you can exploit all that. For example, that checkerboard pattern, you won't have much correlation in 8 by 8, but if you have, I don't know, a very smooth signal, you can maybe increase your block size and get even more benefits in terms of decorrelation, right? Because higher the block size, it will push more things into the lower frequency component. And the second thing it exploits really is that blocks are not independent. So that was another very basic limitations, and both of these limitations carry over straight away from transform coding basics and quantization basics we have talked about, right? Bigger block size, variable length block size, you can do different things. Your blocks are not independent. You can maybe use them to predict. You can use predictive coding, so as to say, to even compress better. And so we don't have to go into details, but this is what the image compression for JPEG again looks at. The 137x, where it was horrendous. And if you do it by BPG, where you allow for all these variable length blocks, predictive coding, as well as, what was the third thing? Larger block sizes, then you can get this image at 8 KB. Now you can clearly see these two are at same sizes, but basically what I want to highlight is there is like a lot of space to improve compared to like just the JPEG in terms of quality. And yeah, so I just wanted to show you guys one thing. Not this. Interesting, yeah. So this is just some example of this bunny image, and this is for BPG. You can now see that there are different length block sizes, right? Like, so when you found a huge constant region, you could increase your block size. Where there was more changing stuff, you could reduce your block size, so that better exploits like the rate distortion. You can better exploit the water filling. And the second idea was of predictive coding, where if you think about these two blocks, they are exactly the same. They are almost the same. So maybe I could just store, the previous block, and that has already done most of my job, even in terms of transform coefficients. So I have to save even less pixels. Just to highlight like how BPG exploits these things. Again, based on this very simple example. And cool, so what's next? So in next class, we'll go over some learned image compressor. So after the Thanksgiving break, so you have Thanksgiving time. Homework 4 won't contain any other content from the future lectures. So it will contain content up to today's lecture. In the next 3 classes, we are gonna go into a bit more advanced concepts. And so come with the mindset of like really enjoying and learning and seeing what we can do better. So the first idea really is we have been really artificially been stuck with the idea of linear transforms. Maybe we can go beyond linear transforms to improve our compressors even further. So far, we haven't even given it a thought in the transform coding world. And the second, in JPEG, you saw that there were like a lot of these hand designed parameters, like, I'll go to YUV, I'll downsample UV by 2, I have these fixed quantization metrics. Think about it, that fixed quantization matrix, it's hand designed for each particular rate. So each of those 64 values, somebody decided I'm gonna put a 13 there, right? Which doesn't seem like we should be able to do something better. And so the class after the Thanksgiving, we're gonna go over learned image compressor, which essentially extends the idea of image compressor based on these two ideas. Yeah, thank you.